Myself, Dr. Amita Asthana from AKGC Ghaziabad. So, we will discuss in this video lecture the very important topic, clippers, and it is from Unit 1. So, here we will discuss the few important points of clippers. See, clippers are very important question, and they are being regularly asked in the main examination. So, now first of all, we will understand what are clippers. Actually, the clippers are the circuits which have ability to clip off some portion of the given input waveform. Whatever input you are giving, and a part of input which you are not requiring, you can clip it off from the clipper circuit. So, the main components which are required for making the clipper circuit is we will use one resistor, one diode, and in some input voltage. Diode may be ideal diode, it may be your a silicon diode, it may be your germanium diode. If it is ideal diode, the knee voltage will be 0 volt. If it is silicon diode, the knee voltage will be 0.7 volt, and if it is germanium diode, the knee voltage will be 0.3 volts. Depending on the orientation of the diode, we will find out whether your diode is positive for forward bias or reverse bias. So, which part of the waveform would be clipped off, that we have to decide. This is the main part of the question, where we are deciding which particular part of the waveform, given input waveform, is being clipped off. It consists of linear and non-linear elements. Linear elements are the resistance, and non-linear the element is diode, obviously. There are two categories of clippers. So, what we can see that clippers, there are two basic types of clippers. First is the forward series clipper, and second one is the parallel clipper, as it is written here. There are, right? Now, simple series clipper. So, this is a kind of clipper circuit. This is input waveform. A sinusoidal waveform is being given. The highest maximum point is Vm and minus Vm. How you will find out it is a series clipper circuit or a parallel clipper circuit? When the output waveform, VO output voltage, that means it is asked between the resistance, it is series. Always remember this particular point. And this is the diode, and since it has not been mentioned in the question that the diode is of silicon or germanium, you can consider it as ideal diode. When the diode is forward biased, it behaves as a short circuit, and when the diode is reverse biased, it behaves as a open circuit, right? Now, this is also series clipper because the output voltage is being asked between the across the R resistance. Now here, why this is called as bias series clipper? Because in the previous question there was no DC voltage, but in this question you can see we have applied some sort of voltage V. Now, how to solve these type of questions? Let us assume few values, and then we will solve a series biased clipper. So, whatever the we will take some values. Take it as 8 volt, minus 8 volt. Now take it as 2 volt. Take this as silicon diode. The cut-in voltage would be 0.7 volt. Now we have to draw the output waveform. This is the question. So I have changed a bit this particular question. Now we will understand how to do. So now we have to see when the diode is forward bias and when the diode is reverse, right? So we have to see and we have to decide these 2 points. Now we will observe this particular circuit. So see, this is a silicon diode. It requires 0.7 voltage to remain in the forward bias condition. So here we will see. Now this is 2 volt and this is making it absolutely reverse. This particular battery is making it reverse bias, right? Now at the positive waveform, this is making it as forward bias and this particular battery is making it as reverse bias, right? This we can readily solve from this circuit. Now when the diode is forward bias, then when this voltage would be greater than 2, this battery effect, DC battery effect will be vanished. When this voltage will go above 2 volts, the battery effect will be vanished. Now after vanishing the effect of the battery, 0.7 is more required for silicon to be in the forward bias condition. 0.7 is voltage is being required by the silicon diode to remain in the forward bias condition, because silicon diode requires a bit more 0.7 voltage. Okay, so here the case 1 we will make. When input voltage is greater than equal to 2.7 volts, the diode is forward bias, right? Diode is forward bias. So when remake the circuit, forward bias. And when the silicon diode is forward bias, it behaves like a battery. Here I am talking of this particular part of the waveform. This, okay. Consider it as plus minus. Now, what would be the output voltage? We will find out. Now, apply KVL. Plus VI minus 2 minus 0.7. Take it positive, minus positive upwards and negative downwards is equal to VI, right? So VU, one equation comes out to be VI minus 2.7. Put it as equation number 1. Okay. So case 1 is solved. We will use this equation while making the graph. This is the process how we have to continue, right? Now, next case 2. When VI is less than 2.7, the diode is reverse bias. And then we will again make the circuit. Now diode is reverse bias. VI. I am talking of this particular part of the waveform. Here and this thing. 2.7 and minus. Okay. So this the part of the portion of the waveform which is below 2.7 volts. Now, what I want to find out VO. Since there is no current, it is open. So VO is equal to 0 volts. So now we have solved this question. Always remember, whenever you are solving a Clipper question, you will make the waveform, make the total circuit in both the conditions, when the diode is forward bias, when the diode is reverse bias, and solve the question. And you will definitely get the answer. If you will make the circuit in both the cases, then you are going to get the answer, right? Yeah. What we have to do is, now we have two equations and we want to, because we have to draw the VO. Now I will erase some part and then I will draw the waveform. Okay, so draw the waveform. -8 +8 and mark your line 2.7. Above the 2.7, it is Vi minus 2.7. Whatever the point here, it like draw a rough sketch. Always draw a rough sketch of the waveform like this. This point will come down by 2.7. So this point will come down by 2.7. This point will come at this particular. This point will drop down by 2.7. So the final points will be this. And rest, all part of the waveform, the voltage is coming out to be 0 volt. So the final answer is this particular waveform. So you have to make the cases and then you have to solve the question, apply KVL and draw the waveform. Similarly, we can have a series clipper, or already we have done. Now we will, there are some example of series clipper and you can solve these questions on your own, and case 1 and case 2 will remain in such a way only. Now coming to the second part of the parallel clipper. So here in the previous case we were taking the output voltage across the resistance, but in this you can see the output voltage has been asked across the diode. So this is an example of parallel clipper. Whenever the output voltage is taken across the diode, the question will be of parallel clipper. The fundamental will be same. So this is a kind of simple parallel clipper. Now if I add one battery in the circuit, then it is a biased. The diode is being biased by this particular DC voltage. So this is also biased parallel clipper. Similarly, we can have such question. Let's say this particular, we will assume few value and then solve the question. Okay. Let's say this is 2 volt. This is making it reverse. Okay. Because the positive side is above and this end side of the diode is downwards. So this battery is making this diode as reverse. Let's say this is 5. This is a normal diode. When this particular part is making the diode in forward bias condition, this is making it forward and this battery is making it reverse. So this voltage needs to win this particular battery. When this waveform will win the battery, when it will be above 2 volts, when it will be above 2 volts. And let's say if it is a silicon diode, then the waveform will win the battery above, win the battery and give silicon 0.7 to be forward bias. It would be 2.7 volt. It should be greater than 2.7 as in the previous case. If it is a germanium diode, then the case 1 would be the waveform should be above 2.3. So case 1 would be when Vi is greater than 2.3, and for germanium when Vi is greater than 2.7 for silicon diode, and when Vi is greater than 2 volts for ideal diode. In this particular case, the case 1 would be Vi is greater than equal to 2 volt, and case 2 would be Vi is less than 2 volt. You will remake the circuit. Here the output voltage will be equal to 2 volt, and here the output voltage will be Vo is equal to Vi. and you will definitely make the graph. So this is how we will proceed in this way. If I want to draw this particular graph, I can also draw. Above 2 volt, it is constant, otherwise it is V1 is equal to Vn. This is the waveform which will come in this particular case. Okay, so you have to do this question. There are again one more example is given. So there are few more examples for all the output voltage are being taken across the diode, and hence we can say we can make for all these 6 numericals, case 1 and case 2, and get the answers for the questions, right? So we have where we can have more circuits where 2 diodes are involved, and here let's say for positive waveform, this diode is, this one at a one time, this is let's say 2 volt, and this is let's say 2 volt, both are at 2 volt, then this Vm should be greater than 2 volt to supersede the effect of this particular battery, and for that time this diode will be off, and when this is in the reverse, this will exceed minus 2 volt, and then the diode will be off. So here the waveform will come like this. You make the cases and solve for positive half of the cycle, for negative half of the cycle, for above +2 and below -2. There would be and there are 3 cases: Vi greater than 2 volt, Vi less than -2 volt, and Vi is okay, like this. If you want, you can, for reverse, you can always, do that in this way, right? So here you can proceed like this for the different type of questions of clipper, and there are 3 categories only: series clipper, parallel clipper, and clipping at 2 different levels. So keep practicing the clipper question and try to make the cases and make the circuits for every case, and then solve the question. Thank you.